Hi everyone, here we are in section 10.1. We're in the antimicrobial treatments topic, and this is the first section for that. So in this, we're going to just focus on some of the things that are really important about antimicrobial treatments and resistance, and hopefully some things that you can relate to. The first one I have on here is state the main goal of antimicrobial treatments and some of the characteristics of an ideal antimicrobial drug. So if we just start off with that definition of um, what is an antimicrobial drug? This is going to be, first of all, a drug. We've talked about microbial control, and we've talked about physical and chemical controls and controlling microbes on the surface of the body on different inanimate objects. But when we're talking about drugs, we're talking about using microbial control within a living organism. So you can imagine that the level of standard of safety for something you're putting inside of the body is much higher than what you would be putting on an inanimate object or even on the outside of the body. So antimicrobial drugs are chemicals that we're going to use inside of the body and are antimicrobial, or killing microbes or inactivating them in some way. And probably, so it says state the main goal of antimicrobial treatments. Well, the first one is to kill microbes inside the body. But there's plenty of things that do that, and many of them are very deadly. So the very first and probably the most important thing about choosing an antimicrobial drug is it needs to be toxic to the microbe, but not toxic to the host cells. And we talked a little bit about this earlier in the semester, where we were saying things like bacterial cell walls are great targets for drugs, for antimicrobial drugs, because bacteria have peptidoglycan, they have cell walls, but we don't. So that drug wouldn't interfere with our cell wall synthesis since we don't have cell walls. And so we talked a little bit about how ribosomes are different in bacteria than they are in eukaryotic cells. So again, bacterial ribosomes can be a great target for antimicrobial drugs. So it would be toxic to the microbe, but not toxic to host cells. And so this is the table from your book. There's all sorts of things that are characteristics of an ideal antimicrobial drug. Microbicidal rather than microbistatic, to actually kill the microbes rather than stopping their growth would make it more effective. You can read some of these others, but one of the big ones here we have does not. Oh, here we go. Remains potent for long enough to act and is not broken down or excreted prematurely. So these must be chemicals that stay in the body long enough to work on the microbes. Does not lead to the development of antimicrobial resistance. We're going to be talking a lot about that in this lecture, and you're going to find that this is a very difficult standard to try to achieve consistently. Complements the activities of the host's defenses. Let's see, can be delivered to the site of infection, and that can be tricky because things like you have an infection in the brain, it's hard to get drugs up there. So sometimes finding the right drug an antimicrobial drug to treat an infection in the brain can be incredibly challenging. Does not disrupt the host health, causing allergies or other problems. So I would say if I had to give the main thing, it would be toxic to the microbe, but not to the host cells. But all these other things are really important supporting characteristics when you're developing an antimicrobial drug. The next learning outcome that I have on your handout is distinguish between antimicrobial and antibiotic. And so the vocabulary can be pretty confusing, and a lot of the words sound alike. And so here's a table from your book. And in here you can see there's the vocabulary word antimicrobial, antibiotic. If you read the section on antimicrobials, it uses that word kind of as a general term. An antimicrobial, it says it's an all-inclusive term for any antimicrobial drug, any drug that it works against some kind of microorganism, regardless of its origin. So you could have an antiviral drug that's an antimicrobial, or an antibacterial drug that's an antimicrobial. So antimicrobial is kind of a general term. When we get to that word antibiotic, it sounds like against living things, and that's where the term came from. But the original term antibiotic came from substances produced by the natural metabolic processes of some microorganisms that can destroy other microorganisms. So it says generally the term is used for drugs targeting bacteria and not other types of microbes. Typically, we use the word antibiotic for those drugs targeting bacteria. And the original antibiotics were produced by living organisms. So the very first antibiotic that was discovered in 1928 by a scientist named Alexander Fleming, and he discovered penicillin. And penicillin was being produced by a mold and it killed bacteria. So that fits our definition of an antibiotic, a substance produced by natural metabolic processes. The fungus produced it, and it can inhibit or destroy other microorganisms, can inhibit or destroy bacteria. So this definition of antibiotics is kind of the traditional definition, but it has changed over the years because what has happened is people or scientists have taken these antibiotics that were first naturally found, and then they brought them into the laboratory and they chemically modified them and they made these semi-synthetic drugs. So sometimes you'll hear about penicillin, but then you hear about amoxicillin that's a little bit different, but kind of the same thing. And a lot of times it's because they've taken these natural antibiotics and changed them a little bit in the laboratory, and we call these semi-synthetic drugs. And sometimes completely synthetic drugs. We understand how these antibiotics work, and they can actually make something in the laboratory that does something similar, but maybe a little bit different, that's synthetic. You might hear all of these called antibiotics. This original definition is what we started off with, but all of these are considered antibiotics today. Here we have the next learning outcome. It says identify the sources for the most common antimicrobials. And here's a picture from your book. And when Alexander Fleming discovered penicillin, what he noticed was something like you see on this plate. And I've seen this repeatedly in the lab. I see it all the time. If you take some bacteria and just spread it on an agar plate, so all this cloudiness in the background is bacteria, and these colonies right here are also different kinds of bacterial colonies. Now, what you notice on this plate has been growing, maybe for a few days or a week or whatever, and what you notice is there's a clear zone around some of these colonies. And that clear zone is what Alexander Fleming noticed when his penicillin was growing, his mold, and it was killing the bacteria in the background. And so what he noticed when he saw this was this microbe is producing some chemical. And that's what he ended up discovering as penicillin. So there's some chemical being produced. And it's kind of interesting because many, many scientists probably saw this before Fleming did. Like I said, I see it in lab every semester. It's something, if I take some bacteria, usually from the soil, and I spread it all over a plate, I'm always going to find some colonies that there's a little clear zone around it, and we have some bacteria making antibiotics. So I said a key word in that last statement. I said, when I take some soil, and it turns out one of the most common sources for antimicrobials are soil microorganisms. And your book mentions bacteria in the genus Bacillus and Streptomyces. These are common antibiotic producers. You do not have to remember the names of those genera of bacteria, but I know that these are Streptomyces because they have this kind of white fuzzy appearance, and they're actually bacterial colonies. But a lot of our antibiotics were found in microorganisms that were originating in the soil. And you can find that a lot today, but all the easy ones have been found. So sometimes you have to be a little bit more creative in looking for antibiotics. This one, this little picture, this was in your textbook, and I thought it was a good bit of history, because what this was is Alexander Fleming discovered penicillin in 1928, but we didn't actually use it until the 1940s in large amounts. And what was going on in the 1940s was World War II. And so here they're saying a race against death. We need to build this building faster. And so what they were doing is building buildings and taking over buildings and just growing shelf after shelf of mold cultures. And from those mold cultures, they were extracting penicillin. Now, fortunately, we don't have to grow mold in giant facilities anymore, because we've been able to extract penicillin from the mold in much more efficient ways than we used to be able to. But this was a great, very serious, important effort during World War II. The last, let's see. Oh, that's where I'm going to stop that right there. Explain that, and we're going to explain the concept of selective toxicity in the next video. Thanks.